lot. And of course, I wanted to, since this is the last talk of this session, so I also wanted to thank the Academy on both our behalf to, giving us the opportunity to actually hosting and organizing this session, and also inviting us to speak in it. We didn't invite ourselves, just for common knowledge. So thanks a lot. And of course, we have heard about NMR, we heard about spin, we heard superconducting. So we cannot leave photons far behind. And so this is our, the last but not least, we'll talk about photonic quantum science and technologies in this talk. So I am, of course, from the Raman Research Institute in Bengaluru, and I head what's called the Quantum Information and Computing Lab. So our lab, So our lab, this is how, snapshot of different experiments would look on a certain day when they're getting photographed. But then, at the moment we have to do with this because these visits are not quite allowed. What we work on is, different applications, both from a fundamental science perspective as well as a technology perspective of photons. So, of course, it's easier said than done to actually work with photons at the single photon regime. So we work with single photons and entangled photons and so on. And so there are different ways in which they can be actually manufactured. And so if people are interested, do have a look at this review article that I was invited to write, where we have covered different types of photon sources and their pros and cons and so on. So we at RRI work on what is called spontaneous parametric down conversion based photons. And here you have these very popular entangled photon rings from down conversion, whereas this particular point here tells you about the entanglement. And we are one of the first labs in the country to actually make these photons and apply them to different applications in quantum science and technologies. So some of our interests I would go over in the next couple of minutes and then zoom in to two of our most recent experimental results for the rest of the talk. We have a lot of interest in working on different aspects of fundamental tests of quantum mechanics itself. And of course, once we understand these principles better, they also help us in applying them to technologies better. So here on the left, you have a series of work we have done where we have actually found, both theoretically and also experimentally for the first time, the correction term that is required to the superposition principle when it's applied to interference experiments. And this is something which has ramifications as tests of Born rule as well as a test of higher order interference in quantum mechanics. And so this is our experiment at the Bengaluru Observatory, which is 100 kilometers from RRI, where we did the first microwave experiment to find this correction term. On the right here, we have some snapshots of our experiments in fundamental quantum optics. This is our take on the very famous Hongo-Mandel interference. And the next reference here is something I'll talk about in detail, which is our new quantum state estimation experiment. We work on entanglement measures and dynamics of entanglement. We heard a little bit about how, somebody else speak. Okay, yeah, we heard from Kavita about, how we want to hold on to entanglement, how to preserve entanglement. So this is our, efforts towards preserving entanglement for longer. And this is the experiment in progress for manipulating what is called the sudden death of entanglement, where we are actually going to hold on to the sudden death, the entanglement for longer and prevent the sudden death. And we are almost done with the experiment. The theory was already proposed by us in these earlier publications. And so this will be a very nice test bed which can be used by even other technologies to preserve entanglement, not just photons. It will be a photonic test bed which can be borrowed by other schemes as well. We are, of course, working on different aspects of quantum measurements, as any lab which does quantum, science and technologies would do. And this is, our series of work that we have been doing in what is called generalized measurements or weak measurements. Now, this is a very interesting area. If you measure a quantum state, you're told that, you kind of change the state. And so then that's the end of the state as you knew it earlier. So you can't really do anything between preparation and measurement conventionally in the von Neumann sense. But if you do what is called a weak measurement or a weak interaction followed by a strong measurement, then in a statistical ensemble sense, you can actually find out what happens to the state between preparation and measurement and derive and explore many interesting properties which otherwise you wouldn't do in the strong measurement regime. And so we have, for instance, measured the expectation value of a non-Hermitian operator using this technique. And this is that experiment, from the lab. In quantum computing, we are following a completely different approach from the ones that we have been hearing so far, which are all qubit-based approaches. We heard about the importance of 2 to the n, where n is n being 50 kind of gives us what is called quantum supremacy and so on. But it took us decades to reach this 2 to the 50. Why is that? Because it's difficult to put qubits more than a certain number of qubits together in a coherent superposition because decoherence kicks in. And so one alternative approach to that could be that instead of using qubits, we use higher dimensional states. That is, qubits as they are called, where n is greater than 2. So qubits, qquarks, and so on and so forth. So there what will happen is, with a smaller number of systems, we can achieve the same dimensionality of the state space as you would do with a larger number of qubits. And this is what is called higher dimensional quantum computing. And it also has advantages in terms of being more robust to noise. Even in QKD, higher secure key rates are possible theoretically. So there's a lot to explore in this from an experimental domain. And this is our picture from the lab where you have our bipartite Q-crypt system, which we have made by using what is called the pump beam modulation technique, which we have actually devised. And so here these are nearly maximally entangled Q-crypts. And also very interestingly, we have found new measures of entanglement for these higher dimensional qubits by relating statistical correlation measures to measures of entanglement. So instead of doing quantum state tomography and deriving that measure, you can do this by using measurements in a complementary basis. So it basically makes things much easier and much more robust from an experimental perspective. So these references have details of that. And also the Scientific American article where I have given a general perspective on our work in higher dimensional quantum systems. Now, going on to the first main topic I wanted to cover, this is our most recent experiment, and this is an experiment in which we have come up with an alternative way of estimating or measuring the quantum state. Of course, at the very beginning of everything, you have the quantum state, and only after that you apply the gates to it for computing, or you apply a QKD protocol. But whatever you want to do, you first have to start with the quantum state. So how do you know what is the quantum state you're dealing with? The most conventional way of doing it is what is called quantum state tomography, which also we heard a little bit. But then having said that, what we have come up with is what is called quantum state interferography, which is an interferometric method using which an unknown quantum state can be inferred from the visibility, phase shift, and average intensity obtained from interference patterns. Okay, so this is a completely new approach to quantum state estimation, and actually, as we will see, it has several advantages over quantum state tomography. And of course, this of course is coming from a fundamental science perspective, but has applications in the technology because any technology begins with the quantum state, right? So quantum state tomography is the standard method for characterizing unknown quantum states. Now, as you know, for a d-dimensional state reconstruction, quantum state tomography requires d²-1 measurements, okay? And for pure state, the best so far has been reducing it to 5d-7 measurements. For our method, which is quantum state interferography or QSI, for a d-dimensional pure state reconstruction, we require d-1 interferograms. And so d-1 interferograms are enough to give us the information required to reconstruct the state, as opposed to the d²-1 measurements that are required in QST. And this, of course, as you can see, gives us a tremendous scaling advantage as we especially go to higher and higher dimensions. QSI does not require any change in experimental setting during the process of measurement. So you have the incident state, you have the state determining device, which is our interferometer, and then the reconstructed state. So this is indeed a single shot state estimation technique using interference. Okay, and so of course a little bit about the theory. So this is a pure qubit state, and this is how you would represent a mixed qubit state, which is the density matrix. So as you know, we will require three parameters to be determined in order to give us the state, which is the theta, the phi, and the mu. The mu is the parameter which determines the mixedness. Okay, and so all these three we are going to determine from one interference pattern. Okay, and so a little more detail. So this is your interferometer. And so the operation that we apply is in fact a projection operator in this arm and a sigma x in the other arm. And then you can work out the math, which I will skip for this current talk. You can find out that the interference pattern, the ID, the pure state is this. And of course, it depends on theta and the phase. And for the mixed state, you also have the mu dependence coming, which is the mixedness. And so after going through all the math, which is there in the reference for you to see later, you can see that there are these three quantities which we can derive from this interference pattern, which is the phase shift, the average intensity, and the visibility. And by doing this, we can reconstruct the unknown quantum state. So this is your Mach-Zehnder approach, where we have which we have not used actually in our experiment. We decided to go for a displaced Sarniac interferometer with a non-collinear geometry, because this actually avoids the extra stabilization that is required in a Mach-Zehnder interferometer. And so here we have done a displaced Sarniac experiment for polarization state interferometry. Our source is a helium neon laser, and the state that we are reconstructing is created by applying a half-wave plate at an angle alpha and a quarter-wave plate at an angle beta to the initial state V. Of course, we wanted to show it for all possible states, that we are able to reconstruct. Otherwise, we could simply use V and show proof of principle, but we decided to go for the entire range of states in the Planck sphere. And so we took different, these are your interference patterns that we have measured, and so raw data versus the fit. And so this is, for instance, the phase shift as a function of alpha and beta. So we have, sampled all possible values for alpha and beta for the phase shift. Similarly, the average intensity as a function of alpha and beta. And then this is the visibility as a function of alpha and beta. So essentially, if you go to the results, so you can find that, if you wanted to reconstruct, we have been able to reconstruct both the mixed state as well as the pure state. And so for the pure state, our fidelity, average fidelity is between 97 and 99%. And for the mixed state, it is between 90 to 98%. As you can see, most of them are above 95% fidelity. So we have a very nice method of estimating the quantum state by using interference as a tool. And we have also shown in this paper how you can extend this for quantum state interferography for a qubit, which is a higher dimensional system. And so now, going to a bipartite pure qubit, that also you can infer by using QSI. And so here, I won't go through the details, but you require only 2 settings in QSI to do this, compared to 9 settings that you would require for quantum state tomography for a pure bipartite qubit. And this is the, detailed math for this. But then having said that, what is important is, as you may remember, the entanglement of a pure bipartite state is, of course, given by this entanglement entropy. So if once I'm able to reconstruct the state, I can also measure the amount of entanglement that this bipartite qubit has. And so in fact here, if I make the assumption that it is pure, then I can do this by only using the rho B reconstruction. So in fact, by a single setting, I'm able to quantify the entanglement also of a bipartite pure state. So QSI can be used to determine an unknown qubit state using a single shot measurement. If a bipartite state of qubits is known to be pure, QSI can quantify the entanglement with a single setup. With 2 interferometers, any pure qubit state, d greater than 2, can also be determined. So the d-1 interferograms, as I mentioned, is required. But then you can also map it to only 2 interferometers, so either a spatial mapping or a temporal mapping can be done. So it gives us a very, very good scaling advantage over conventional quantum state tomography, and can be used for quantifying entanglement of a pure bipartite state. So this is an example of an experiment that we have done, where we have, of course, used one of the most fundamental quantum physics applications there could be, which is interference, right? That forms the basis for most things we do in a quantum domain. And we have used this as a resource yet again in a completely new avatar, and come up with a technique which actually very well competes with quantum state tomography and beats it on many accounts in terms of the scaling advantage. And so, so this is one example of a very recent experiment. The second thing I wanted to talk about is quantum communication. Now, all 3 talks in the session so far have been related to either quantum computing or quantum information processing protocols. So in order to give this session a holistic feel, I wanted to concentrate on our work in quantum communication for the rest of the talk. And in fact, what is quantum about quantum communication is, of course, the key distribution itself, which is called quantum key distribution. And quantum key distribution can definitely be called the most quote-unquote practical quantum technology, because it's definitely been established. It is out there. It is being used by various companies as well, and strategic organizations, as opposed to, let's say, the quantum computer, which is still at a research level. why you should worry about quantum communication. Of course, if you're invested in any of these applications, let's say purchasing something with a credit card, online banking, electoral polling. Now the entire world is waiting for that one election result. And so if I voted for party A, I don't want party B to actually get the vote in a malicious way. And so these are all examples of strategic communication, which in fact are currently being done through what is called classical cryptography. And these are at a risk of being compromised with quantum computers. And so the solution that we need to come up with now also has to be from the quantum domain. And that solution is quantum cryptography. Okay. So what is wrong with classical cryptography? The problem is that unconditional security is not possible. So for instance, this RSA protocol, which forms the basis for many of our classical crypto systems, is based on the mathematical complexity of factoring large numbers. Now, Peter Shor here came up with what is called the Shor's algorithm, which using quantum gates can perform factorization in polynomial time. Thus, that means that the factorization problem now becomes much simpler than what it is on a classical device. And so then what happens? So what happens to the security? Computational resources grow very fast, and today's hard problem could be solved tomorrow using brute force attack. New algorithms can come up for classical computers. We can have realization of quantum computers. So my security should be independent of future advancements in computational power, new algorithms, or new technology. That is, it should be future secure. So this brings forth the need for quantum cryptography, where security is based on laws of nature, or laws of physics, and not on the mathematical complexity of a problem. And the most important part in quantum cryptography is quantum key distribution. So now if I look at the current, scenario, if I wanted to break this RSA, 2048-bit key length, then that would actually take apparently 1 billion years with a classical computer, according to Microsoft, and 100 seconds using a quantum computer. But the catch is that in order to do this, we would need 4,000 qubits and 100 million gates. So, of course, a skeptic would say, we don't really have that many qubits and that many gates, so why bother about quantum cryptography? But that's, of course, a wrong notion, because you see, the quantum computer will make many things way better for us than what it is currently. So we don't want it to pose a challenge to security unknowingly. So we have to come up with a solution today so that tomorrow when the quantum computer with this sort of resources comes in, it is not a problem anymore, because we already have the solution which is working well, which is quantum cryptography. That is why complacency is not going to be advantageous. And so regarding quantum communications at our lab at RRI, we have several ongoing projects. One of them is called Quantum Experiments Using Satellite Technology. And this is in fact India's first project on satellite-based QKD towards long-distance quantum communications. We are working on integrated photonics-based QKD, which is a chip-based QKD in collaboration with Italy under the ITPA program. We are also working on a project under the DST Quantum Enabled Science and Technology program towards long-distance quantum teleportation. And we also have a project under the Center for Excellence in Quantum Technologies of MIT on device-independent random number generation, which of course is a very important thing to establish towards security of communication among various other things. So quantum mechanics, how does it protect information? Well, the idea is that there are several principles in quantum mechanics, like the uncertainty principle, the no-cloning theorem, and quantum entanglement, which are used as the basis for protecting the information in quantum key distribution. I won't go through the details of how for the stop, but of course, this is the general idea. And there are different approaches to QKD. There are prepare and measure-based approaches as well as entanglement-based approaches. Entanglement-based approaches are important to go towards what is called device-independent QKD, where we do not even trust the device anymore, let alone any adversary. Even if the device manufacturer is an adversary, that also is not a problem for entanglement-based protocols. So in our lab at RRI, we are working on all these approaches, both prepare and measure and entanglement-based QKD. The prepare and measure is performed using single photon sources, using this uncertainty principle for the security. And this is our experiment from long ago on the BB84. But the recent one that we have done is actually our take on what is called the B92 protocol, which is a prepare and measure based protocol. And this is a snapshot of various, Alice and Bob modules in the lab. And in fact, this is a very, important demonstration, not only because it is a much more secure demonstration than the earlier ones where they did B92 using heralded photons, but also, in fact, this happens to be India's first free space end-to-end QKD experiment which has been published. And so this is very important for us because this paves the way towards longer distance for us. And so this is within the lab 2-meter distance where we have achieved the end-to-end QKD. And so this is our the details. This is the photon source schematic, and this is the Alice and Bob setup. What is important here is you can see the key rate that we have achieved is around 50 kilobits per second, and a QBAR, which is a quantum bit error rate, which is less than 4.8%. And why is 4.8 important? Because 4.8 is what is called the information theoretic security threshold for the B92 protocol. So you have to perform a lot of intricate calculations using information theory and set security thresholds for different protocols. And only if your implementation is below that in its error, then it is a good candidate for being used for the strategic secure key purposes. Otherwise, it's not. And so this quantum communication is a very interesting domain because it involves fundamental physics, it involves hardcore information theory calculations, as well as ingenuity in device applications as well as engineering. So it's kind of a marriage between various things possible. And of course, as I said, to our knowledge, till date, ours is the best available B92 setup because we have the best so far was 31 kilobits per second and a QBAR which was way higher of 10.5% for a smaller distance, so using an SPC source. And we are also working on entanglement-based QKD. This is a schematic of one of the entangled photon sources we are using, and this is how it looks, the BBM92 protocol. And we have achieved a very, very nice concurrence of 0.995 for our entangled photon source, and our key rates and QBAR are also very, very good for the entanglement-based QKD. One of the other developments which has happened along with this, this end-to-end QKD experiment is the development of a simulation toolkit for QKD. And in fact, as I speak, my students are currently at this, this Data Security Council of India. They are organizing today a road show on national, cyber security. And so we are presenting this work there. And I kind of have taken a 2-hour break and because I'm here at this event. And so we are presenting this there as we speak. And so this is a very interesting toolkit, and I'll explain to you a little bit about why. And so this is the reference, because it's a very detailed thing. So please have a look if it interests you. Also caught some public attention, so the IBM blog and so on. Anyway, so there are different simulation toolkits which do exist for QKD literature. These are the ones you will find if you do a search for them. But what is interesting is that our requirements which are in fact the following, that is, we want a quick and precise simulation of physical processes considering realistic experimental imperfections. We want to simulate the source, the detection module, and background noise in more detail, and have this generalization and applicability to all existing protocols. These are not met by any of these toolkits. And why is that? Because you see, most of these toolkits, they are developed by software developers, and they don't really care that an experiment is never going to be ideal. It's people like us who are working in the lab who know that a beam splitter will never be 50-50 even if you wish it to be, and a detection will never be 100%. So whatever you get out, as a result from these toolkits are going to be way too ideal to match with your actual experimental output. And we wanted something which does that. Because you see, with QKD becoming more commercially viable, advanced engineering techniques are being proposed. And if you want to now directly test these techniques in an optical setup, it won't be very cost effective. You want to have a simulation toolkit which considers these imperfections first and then spend your resource. And so that is what we have done, used this QKD sim. And we have tested its prototype with our own implementation of the free space B92 protocol. And we have followed what is called the AGIFOL model of software development. Again, details to be found here. And the match between simulation and experiment, of course, is very heartening because, they are in the same order. And of course, QBAR is restricted to be below 4.8%. And now we are already working on a new iteration where we are including even more imperfections and a greater applicability to protocols. Our lab is actually focused towards long-distance quantum communications. And of course, while my student and I talk to each other using a quantum communication channel in the lab, which is 2 meters, that's not enough. The idea is for strategic communications, you need to increase the distance over which this will happen. And in ground-based systems, you have demonstrations typically up to 300 kilometers, because beyond that, you don't have line of sight. And then if you do fiber, then after a certain point, there would be a loss in the fiber. And you cannot use a classical repeater technology because that would violate no cloning theorem. So you have to come up with an out-of-the-box way of increasing the distance for quantum communications. And one of them is using what are called quantum repeaters. And in fact, this is our project in this DST one, where this discussion with Vibhu last talk about memories comes in. But when we are working on entanglement distribution using quantum relays, and then on using satellites as a trusted node. So I'll stick to the satellite part. And the general idea is that if you want to increase the distance over which communication is happening, you have two ground stations here. The satellite comes and exchanges key with one of the ground stations, and then it moves over to some distant point, maybe thousands of kilometers away, and exchanges a key. And by performing some mathematical operations, you in fact end up with a quantum link between these two ground stations, which otherwise would never be connected. And so this is the idea of satellite-based quantum key distribution. And we are actually going towards what is called the global quantum communication network, where you will have satellites connecting distant ground stations, and then these ground stations connecting different service providers, maybe through fiber network. So a combination of free space and fiber will lead to this global quantum communication network. There are different efforts from different countries towards satellite QKD, including, of course, our own. But the only one so far where there is a satellite in space is the one from China, which is the MISSIA satellite program. And so our experiment is quantum experiments using satellite technology, which is a collaboration between RRI and ISRO, and it has been on now for the last 3 years. And we want to have information theoretic secure communication between two Indian ground stations using an Indian satellite, and also have a communication between an Indian ground station and a Canadian ground station to have this thousands of kilometers distance hopefully achieved. And these are pictures from RRI itself, and this is my lab, but these are actually the portable ground stations which we already have for free space communications. And we are performing this over this link across campus. And this is inside the ground station with students and colleagues with this telescope, and so this is the idea of how we do free space communication. So with that, I would like to thank you, and of course thank the Academy again.